Hello everybody, it's Mr. Woodward. In this video, we're going to talk about conservation of energy and how the law allows us to solve some problems if we know how to do the calculations. So as a reminder, the law of conservation of energy states that the total energy of an isolated system remains constant. It's said to be conserved over time. Okay, and that energy can neither be created nor destroyed. It can only be transformed or transferred from one form to another. Okay, energy is conserved. So we're going to take a look at an example here of a woman who's falling from a burning building. You can see this picture, right? She's jumping out of the window very high up in the building, falling, and then down here at the bottom, there's a group of firemen that are catching her in this sort of trampoline. And so this is going to be an example of the conservation of mechanical energy. Okay, so notice that at the top of the building, she's got a total of 10,000 joules of energy. And that as she falls, her total energy remains the same. It's still 10,000 altogether, but now there's a little bit less potential, a little bit more kinetic. Okay, and that as she continues to fall, the total remains the same. The total is still 10,000, but now she's losing even more potential and gaining even more kinetic, right? PE is potential energy, KE is kinetic energy. All the way down at the bottom, when her height is now 0 above ground, she has no more potential energy and 100% of her energy is now kinetic, but the total is still 10,000. Okay, this is what we mean by the conservation of mechanical energy. Energy is neither created nor destroyed. The total energy remains the same, but the forms of energy might change hands between different types. All right, so let's answer some of these questions together using the law of conservation of energy. And then we will just remember that potential energy is mass times gravity times height, and kinetic energy is 1/2 mv squared. And the woman's mass in this problem is 51 kilograms, okay? All right, starting with number one, how high above ground was the woman when she jumped? Okay, well, when she jumped, we see that her potential energy is 10,000 joules and her kinetic energy is 0. So her potential energy is completely related to how high above ground she is. So I'm going to use that to figure out how high she was, starting with the potential energy equation. And this is gravitational potential energy. By the way, there are other forms of potential energy, but we're focusing on gravitational potential energy. Okay, she's got 10,000 joules of gravitational potential energy. Her mass is 51 kilograms. G is acceleration due to gravity on the Earth, and her height is the unknown. Okay, so solving for her height, we get, conveniently, 20 meters. Okay, so she's jumping from a window 20 meters above ground. Continuing on, how fast was she going when she hit the trampoline? So down here, when she hits the trampoline, now you can see that her energy is 100% kinetic. She has no potential energy. So we're going to use that. She's got 10,000 joules of kinetic energy. And so let's use the kinetic energy equation. Kinetic energy is 1/2 mv squared. She has 10,000 joules of kinetic energy. Her mass is still 51 kilograms. And now I'm going to solve for her velocity. Okay, so doing the algebra, v squared is 392.16, and the units are meters squared per second squared, which means that the velocity is 19.8 meters per second just before she hits the trampoline. Okay, so far we've used kinetic in number 2, we use potential in number 1, and now we're going to use a combination here in question number 3. How fast was she going when she was 10 meters above ground? Okay, so her total energy, even when she's 10 meters above ground, is still going to be 10,000 joules, because energy is conserved, right? The total is always 10,000. But now we need to be a little bit more careful and get her velocity from that. So let's take a step back. First, when she's 10 meters above ground, I can calculate her potential energy, right? So at a height of 10 meters, I can say that her gravitational potential energy is going to be mgh, which is her 51 kilograms times 9.8 times a height of 10 meters. And so I get that she has 4,998 joules of gravitational potential energy when she's 10 meters above ground. Okay, now, her total energy is always 10,000 joules. So I can figure out how much kinetic energy she has, right? Because the total is going to be potential plus kinetic. And I know that the total is 10,000 joules. And that's 4,998 joules of potential energy plus some amount of kinetic. So I could just subtract and figure out that at this particular moment, she's got 5,002 joules of kinetic energy. Okay, now I'm getting closer. Remember, I'm trying to find how fast. So I'm trying to find velocity. So now this feels just like the previous problem. I know the kinetic energy, so I can pull the velocity out of that kinetic energy. Okay, so here we go, just like before. The kinetic energy is equal to 1/2 mv squared. She has 5,002 joules of kinetic energy. Her mass is 51 kilograms. And it's her velocity that's the unknown. Okay, so doing the algebra, rearranging, solving for v squared, taking the square root, I get that her velocity is 14 meters per second at this particular moment. Okay, so that was kind of a three-step problem. In step one, I had to figure out her potential energy here. In step two, I had to figure out her kinetic energy because kinetic plus potential will equal 10,000. And then in step three, I got her velocity based on the fact that I knew her kinetic energy. All right, let's try one more. Number 4, how high above ground was the woman when she was falling at a velocity of 10 meters per second? Okay, well, at 10 meters per second, I can figure out her kinetic energy, right? Kinetic energy is 1/2 mv squared. So I've got her mass, I've got her velocity, plugging in the numbers, I find out that she has 2,550 joules of kinetic energy at that moment. So similar to number 3, I'm going to figure out now how much her other form of energy is based on the fact that the total is 10,000. So I can actually take this same idea from above and bring it down here. Okay, the total is still kinetic plus potential, or potential plus kinetic. So the total is still 10,000 joules. Okay, I can figure out how much potential energy she has by subtracting it from 10,000. So she's got 7,450 joules of potential energy. And then let's go back to what we're looking for, right? How high? That's the goal. How high above ground? So now that I've got her potential energy, I'm gonna pull the height out of that. So potential energy equals mass times gravity times height. This is 7,450 joules. Her mass is 51 kilograms. Acceleration due to gravity is 9.8. And I can solve for the heights. Okay, doing the algebra, I get that the height is 14.9 meters. Okay, so let me just kind of recap, right, the big idea here, the big idea. this is always going to be true, that the total mechanical energy is going to be potential plus kinetic, and that the total will always remain the same. Okay, that total is never going to change. So if you want, you could say something like this, that the total at some before moment is going to be equal to the total at some after moment. Okay, and that means that PE plus KE before is going to be equal to PE plus KE after. Or if you want, we could swap out the before and after and just call it like time 1 and time 2 for any comparison. The total at time 1 is going to be equal to the total at time 2, which means that PE plus KE at time 1 is going to be equal to PE plus KE at time 2. And so a phrase that is sometimes popular to see in physics is a longer version of this, which is that mgh plus 1/2 mv squared at time 1, so we would call that, H1 and V1 is equal to mgh plus 1/2 mv squared at time 2. We would call that H2 and V2. And so if it's helpful to you, this form might be worth memorizing or having ready, right? And this is a long way of saying that energy is conserved, right? The sum of potential plus kinetic at some moment in time is going to be equal to the potential plus kinetic at some other moment in time, so that the total always remains the same.